Hello world, here's Jorge, and let's continue learning about object detection in PyTorch. In the last video, we defined a method called compute-oriented gradients, which essentially took an image with that it could actually be either grayscale or 3-color channel, RGB. Okay, so we implemented both options, and we also, for both, regardless of the option we picked, we needed to eliminate the boundary pixels in order to avoid boundary effects. And finally, once we got our gradient ready, we passed it through the orient layer so that we obtained the oriented gradients. All right, and we are also going to return the squared norm, the squared magnitude. Okay, great, that was last video, and now let's actually continue. All right, let's continue learning, and the next step is to implement the angular binding method. Okay, and so let's understand why we need this method and how does it work. Okay, so essentially we have been working with a method that took the gradients and that essentially projected them with respect or onto reference orientations. Okay, so remember that initially we set the number of orientations to be equal to 9. So the compute oriented gradients, what it did was to essentially say project the gradient with respect to these specific orientations based on these angles. Okay, so essentially in this method the gradients were basically passed through the orient layer in order to obtain the essentially gradients classified with respect to the oriented directions, or say classified with respect to these reference orientations. Okay, then this operation told us how well a given gradient is aligned with each orientation. All right, so it gave us a score. We could understand this as having a score associated to each gradient, and the higher the score is, the more aligned it's going to be with respect to that specific orientation, that default orientation, that in this case, of course, is going to be, they're going to be 9, because we have 0, 40, 80, and so on, till 360. Okay, so in other words, it computed a set of projections that told us how aligned the gradient was with respect to each reference direction. Okay, so in other words, as I said, the projections gave us scores for alignment with respect to these. Okay, all right, so what is next after having these oriented gradients and the square magnitudes, right? Well, the next step is to perform an operation that is going to give us a distribution of the gradient magnitudes into the two nearest reference angles. Okay, based on how closely aligned these gradients are with respect to those directions. Okay, so essentially right now what we have is just a bunch of scores that they tell, okay, your gradient is or basically scores based on which we can assess whether a gradient is well aligned with a reference orientation or not. Okay, we can assess it based on these scores that we obtain with compute-oriented gradients. All right, but now with this angular binding method, what we want to do is to go beyond and be able to identify whether a specific gradient belongs or is closest to one neighbor angle or the other. So it's a way to more precisely determine where or in what region exactly is, in the spatial dimension, I mean, where our gradient is located. Okay, it's gonna be able to determine in a more precise way where this gradient is located. Okay, so as an example, imagine we have a gradient of 30 degrees. Okay, so applying this angular binding method, we're gonna be able to identify whether so essentially if it contributes more to the 40 degree bin or to the 0 degree bin, and based on these information we're gonna be able to determine of what angle we are talking about. Okay, because say this information is unknown a priori, in the sense that we can guess the angle based on the say score, that the new score that we obtain in the angular binding, because what we are going to get is a score that's going to tell us, okay, the gradient is closest to 40 degrees and 0. Okay, so that we suspect that the gradient, it needs to be in between, say, 20 and 40. Okay, so it kind of gives us more precise information. Okay, whether this gradient is say close to 40 or 0 degrees. But again, this is just an example. We will understand it as we go through. So this is why we define angular binding, to get this more precise information, because without it, gradients would only belong to a single direction. Okay, so this means that essentially we would have just gradients that would be classified either as 0, 40, 80, just hard binding. Okay, so, and we would not have smooth transitions between orientations, and these could potentially lead to instabilities. Okay, especially for gradients that are really nearby boundary bins. Okay, but yeah, that is the theory. That is, say, why we are applying this angular binding, to get this more precise information about where our angle is located, or what kind of special properties it has. But now let's start coding. Let's start with the fun part. So essentially, how are we going to start? Well, first of all, we need to recall that we're going to use the results that we obtained previously in the compute-oriented gradients method. All right, so that means that we need to have a look at what we obtained. Okay, and we obtain the oriented gradients, and we obtain the squared norm. So the first thing we need to do is to unpack these results. Okay, so that we can actually then use those as an input whenever we see it's convenient. All right, so let's do that. Let's start with doing that. So essentially, let's unpack that. So orient gradients. You can call it different names, right, when you unpack, but let's just gonna call it the same way that I did in the original function. So then compute oriented gradients. Okay, fantastic. So now what we're gonna do is to, well, first of all, before going any further, let's actually import torch. Then we're also going to import math, and also state that the number of orientations that we're using are 9. Okay, and also we're going to define a dummy tensor. So just put random tensor here, random tensor, and we're gonna just state, okay, we can just call torch dot random, and well, remember that we are dealing with a 4D vector, and also remember that we are dealing with 3 color channels in this case. Remember, we could also obtain, okay, oriented gradients for our grayscale images. Okay, because remember that we prepared our compute-oriented gradients function to have both options, to be able to handle both cases. But just to carry on with it, let's continue dealing with the case of having an RGB image. Okay, so that's what we are going to do. So let's continue. So let's put your torch. Fantastic. So we're going to have circular channels, and just to keep it simple, very simple, just a 3x3 image. Okay, and just to keep track of what we do, just print this out. So original tensor and okay, great. That works out. So now we can actually call for random tensor. Run this right there. And now let's see what happens. Okay, so we get these for the tensor. And essentially, what are we getting? Well, first of all, essentially, well, of course, we didn't print it out, so we just observe the random tensor. Okay, so we need to actually let's print, and let's say oriented gradients, or this. And oriented gradients, well, let's call it oriented, right? Fantastic. So now, exactly, we see a bunch of say tensors 3x3 embedded, right? So let's actually have a look at the shape just to recall what you'll quickly remember from the last video. So the shape of oriented gradients is going to be, wait, gradients and shape. And here, put a space. Yeah, exactly. So we get 18. So why did we get 18 in the first place? Well, remember that we are dealing with 9 orientations, but also remember that the compute-oriented gradients took into account both the positive and the negative orientation. Okay, so that means that if we have originally 9 directions, that means that we need to multiply by 2 to also take into account the negative direction of the gradient, like the reference gradient. Okay, fantastic. So that is why we get 18. One say block per possible orientation. Okay, taking into account both positive and negative. Fantastic. So that is just recalling what we obtained, because we're going to use the results in our say a new method called angular binding. Yeah. So that's one thing, but also remember that we had another output. Okay, we just unpacked it. So let's also visualize that. So that was the squared magnitude. Okay, more specifically was the maximum values of these squared magnitudes of our gradients, but I'll just call it the squared magnitudes just for simplicity. Okay, so squared magnitudes or gradient magnitudes and essentially that was N2. That was N2. Okay, and you see that it was just a single pack, and with shape of 1133. Okay, so we just get one, say, set of 3x3 tensors, where essentially all the maximum square magnitudes of a given or the maximum gradient magnitudes associated to a given image are stored in. Okay, right. Fantastic. So that is just visualizing the results that we obtained through the previous method, the compute-oriented gradients. But now what can we do? Well, we can just start defining our, say, a new method. Okay, so let's define that. So define angular binding. Define that. And well, what is going to take? So what arguments or what values are going to be taken by this method? Well, of course, oriented gradients are going to be one. And what else? Well, the squared magnitude. So literally, we are taking as an input the outputs of the oriented, of the compute-oriented gradients method. All right. So fantastic. So let's do that. So N2, and let's get started. So first of all, remember, this is the squared magnitudes of our gradients. So this means that we need to, well, get we want, better say, to get the magnitudes, just the magnitudes of our gradients. To do that, we just need to take the square root, right? So we obtain the magnitude. We obtain the magnitude of the gradients. Okay, so just let's do norms, and we just obtain it by taking the square root of N2. Okay, and just to visualize, let's print it out. Okay, and this is going to be norms. Fantastic. So let's actually, well, of course, if we just hit it right now, we are not getting the output of angular binding, of course, because we need to essentially call the function, right? So angular binding, and here we are gonna input the actualness. Well, remember, I mean, this doesn't need to be called the same way. So just to clarify that, so let's put here norms 2, and let's put here orient gradient, say, just so that you see, of course, that we don't need to take the same name, right? So oriented gradients and N2. Yep. So let's actually see the output. So this is the magnitude of the RGB. Remember that we have all these zeros because we applied the filtering of the gradients on the margins of the pixel of the image, right? And remember that we're dealing with the very simple case of 3x3. image, so that is why we just get just one value that is non-zero, right? Okay, so that is the magnitude of the RGB. And now what else can we do? Well, what we need to do now is to normalize the gradients. All right, so essentially we need to divide them by their magnitudes. That is why essentially we computed the magnitudes just now of the gradients. And not only that, but we need to make sure that none of those values are zero, okay? None of the values within the norm are zero, because if you actually have a look now, because if we just say, okay, let's just define, okay, let's say we were not aware of this, we were not worrying about dividing by zeros, right? So what will happen here? Well, we need to normalize, right? So let's call the normalization factors, right? Normalization factors, and we need to divide by say these norms that we just computed, right? We just need to divide by that. Let's see what happens. You see, we get infinite. Okay, we get infinites because, of course, we're divided by zero. Okay, so this cannot be. So we need to avoid this kind of mistakes. So how can we do that? Well, we can clamp our tensor. Okay, so how does clamping work in Python, or more specifically in a PyTorch? Well, let's just have a look at the actual, say, functionality of clamp. Okay, let's just have a look at that. So PyTorch clamp. So dorsal clamp, essentially what it's doing is the following. Of course, clamps all elements in input into the range that you specify between the minimum and a maximum. So you specify a minimum value, you specify a maximum value, and it's going to respect those as your boundary. And any value that is below the minimum, well, is going to be replaced by the minimum that you input here. And same story with the maximum. Okay. So essentially, we have here a simple example. We have here how a vector, right, a 1D vector, and we are going to clamp it both from the left side and the rest, and on the right side. We're going to have minus 0.5 for minimum, 0.5 for maximum. So look at this. How, well, actually, let's just do it, right? Let's just do it. So just comment this out for now, and let's just clamp it. So if we do torch.clamp, and we need to input the tensor, right? So if we input tensor, so random tensor, and we specify a minimum, say we specify I don't know, minus 0.1, and maximum 0.1, for example. Yeah. Let's see what happens in that case. So look at this. Well, just for reference, let's actually print this in here next to it so that we can compare. Exactly, fantastic. So look at this. We got rid of values that were above 0.5. So instead of having 0.2365, we get 1. Yeah, and so on with the values that are above 0.1, and of course below 0.1. You see how the values are replaced by -1, right? Fantastic. So that's simple. That is how clump works. So let me just comment this out and uncomment these. Right. So now we understand why we cannot do just this normalization of divided by the norm just like that, because we are going to have zeros on our norm, because of course just this is guaranteed, right? Because we removed the pixels of the boundaries and replaced them by zero, so we are guaranteed to have zeros, right, in our tensor. So we need to do this 100%. So that is why we are going to use clamp. So let's do that. So 1 over torch.clamp, and we are going to input the norms. That's our input tensor for clamp. And in this occasion, we only care about not having zeros, right? So we just can set the minimum, right? No upper boundary here. So for instance, let's just set it to a very low value, and non-zero, of course. So for example, 1 times 10 to the minus 15. Yeah, great. So now let's actually visualize this, and actually let me add here strings so that can be better understood. So here. Okay, so let's say here gradient normalization factors. Fantastic. And here let's put a space. Fantastic. So indeed, that's what happens. You see how achieved essentially getting rid of the zeros. Okay, so instead of zeros, we just get this a very small value right there. Okay, exactly. Fantastic. So now we just continue. We are going to continue, and how? Well, what we need to do now is to essentially extract. We need to extract the angles that are associated to the essentially oriented gradients. Okay, and as you'll see, there are 2 ways of doing this. Okay, like the say more proper way, right? The more say more theoretically meaningful way is to just apply the arc cosine. So we can just use arc cosine to extract the angle that is associated to our gradient. However, the problem is that you could face instabilities if you have a very large amount of numbers, okay, to extract the angle from. Yeah, so in order to avoid these instabilities, the other option is to actually simplify these operations, and instead of taking the arc cosine, what you can do is to actually make an approximation of the arc cosine. Okay, so how do we do that? Well, we just need to take the Taylor expansion of arc cosine. Okay, so from, of course, calculus, we know that the arc cosine can be expanded into infinite number of elements, infinite number of polynomials, and then what we can do is to just take the first order, okay, of this expansion. All right, and we are going to see both, right? But yeah, let's get started with this process. And first of all, before we get into the extraction of the angles, we just need to say normalize our oriented gradients, okay? Because here I just defined the say normalizing factors, but I didn't apply them, right? So let's do that. Let's do that next, and what we can do is, okay, I'm gonna call cosines to the normalized oriented gradients. Why am I calling them cosines? Well, because the projection that we applied in the oriented gradients, okay, is actually a dot product. It's say analogous to apply a dot product. Okay, and the dot product is mathematically essentially defined or based on a cosine. Okay, that is why I'm writing a cosine. Well, so cosines are going to be factors times the oriented gradient. Okay, so now we just applied it, and now, well, let's actually visualize that. So let's print this, and let's call this, say, normalized oriented gradients. Gradients. Right, and go here. Okay, fantastic. So let's have a look. Okay, so we have applied the normalization factor to the actual oriented gradients. All right, so we have this result. Well, as you can see, there are most of these numbers are multiplied by a factor of, say, 10 to the 14, 10 to the 15. Okay, all of them. Well, except certain exceptions, like this one, times to the minus 1, and here again, but most of them, you see, are multiplied by a huge factor. Okay, what's the problem with that? Well, remember that the cosine function is bounded between -1 and 1. So this means that these values, as they are right now, they're not going to work for us. They are not going to work because they are not within this boundary. Okay, so we need to be very aware of that and fix it. Yeah, but yeah, welcome to that. So now let's start, and let me first state that there are two possibilities here, two possible methods. So we're so let's see how to, yeah, let's say we're going to choose a method for angular binding. Okay, so there are two options. Yeah, say call it M1, method 1 is going to be using our cosine directly. Okay, we're going to use our cosine as it is. Okay, as simple as that. Well, what is the potential issue with this method? Well, that is going to be slower. Okay, this method is going to be slower as compared to the second method, which is just an approximation of our cosine, that is, take first order Taylor expansion of our cosine. Okay. All right. So those are the methods that we are going to use here. Okay. So let's first get started with the direct method. So let me here initialize variable and call this true. And essentially, let's state that here, okay, oops, state here that this method, just to stress this point, okay, this method is precise. So essentially, of course, more precise than method 2 because method 1 is precisely the formula. However, it's slower, okay, because basically the arc cosine is more computationally expensive. All right, that is the issue. Fantastic. So now let's get started. So if the first method is true, well, we're going to apply these essentially direct formula for the arc cosine. And well, first of all, remember that before we extract the angle, we need to pre-process the data. We need to essentially have all our data within -1 and 1. Okay, otherwise it's not going to work because the cosine values need to be between those values. So let's pre-process that. So we're going to state, so the cosines values need to be between the range of -1 and 1. Okay, great. So all right, so let's actually pre-process our say cosine data. So torch dot how, well, with clamp as well. Yeah, we can actually do that with clamp. So cosines, and we're gonna have -1 and 1, of course. So essentially we're gonna get rid of values that are less than -1 and values that are above 1. Great. Like that, we are ready to extract the angle. So let's do that. So compute the angle. Compute the angle. Let's do it in radians. That correspond, okay, to each cosine value. Yeah. Okay. So essentially, we just state, well, the angles are going to be the arc cosine of the given element. So like that. Great. And now what we can do is to actually visualize. So let me first visualize the say pre-processed data so that we are sure that we make sure that everything worked correctly. Yeah. So I'm going to put here, say, properly, well, filtered or pre-processed cosine data. Okay, let's do that here. And all right, let's visualize this. Okay. It looks like it worked. Okay, because of course we don't see any values that are above or below, or above 1 or below -1. Great. So let's continue. Let's actually write these properly. Pre-processed. Okay. Okay. Fantastic. So now what we need to do is to essentially, once we have filtered, well, we need to compute the angle. So let's actually have a look at those. So let's have a look and state that the angles in radians that correspond to each cosine value. Okay. Okay. Great. So let's also visualize that. Great. So of course we see values that are systematically repeated, and those are 3.14. Of course, that is the value of pi. Okay, that would correspond to 180. Yeah, 180 degrees, and then we also have zeros that of course correspond to 0 degrees. So that makes a sense, and all the values need to be in between. Okay, all values that are different than 0 and 3.14 need to be in between, which is the case. Okay, great. So we just extracted the angles. So what is next for us after we have performed such a task? Well, what we need to do now is to map the angle that we obtain for each, say, gradient, and associated with the weight. Okay, so essentially the idea with this mapping is that we want to have gradients that are going to be closer to a reference direction. Okay, and these, so if that is the case, okay, so if we get a gradient that is closer to a reference direction, well, its associated weight is going to be higher. Okay, while if it's the opposite case, in the sense that if the gradient is farther from the direction, the reference direction, well, it's going to get a lower weight value. All right, that is the idea right there. So let's do that. Okay, we're going to map the angle in radians to a weight. Okay, that is the idea. All right, and well, how are we going to do that? Well, we are going to use the following logic. So we're going to say, okay, by the way, we're going to call these weights bin weights. Okay, bin weights, because again, these weights are going to indicate, all right, that a given, say, gradient is closer or further away to a reference, say, direction. Okay, all right. So what formula are we going to use? Well, we're going to use the logic that we use to obtain the angle, because remember, when we calculated the angle, okay, we did an operation where, say, in oriented gradients, okay, let's have a look. Yeah, here in oriented gradients, we computed the angle by the following formula. We took the say the whole circumference, and we divided it by the number of orientations. Okay, so in here, to get the bin, okay, this factor is going to be say inversed. Why? Well, what we're doing here is to say, I imagine this, right, as having to solve for I, okay, where I, remember, was the orientation, okay, was the the orientation out of the all possible. Okay, so because remember, this loop basically went through all possible number of orientations, and here what we want to do is to solve for I, and if we solve for I, we're going to have basically 2 times number of orientations above 2 times pi, yeah, and that is multiplied by the angle. All right, so we're gonna do just that. And we're gonna do actually 1 minus the factor that I just obtained, that I just explained, okay? And in that way, we're gonna get the bin weights. All right, so let's do that. Two times number of orientations and 2 times pi and the angle. The angle and which, yeah, what's called angles. Great. So now we just obtained these weights, these bin weights, okay? And let's just have a look at them. So, right, and we're gonna have the weights associated to angles, and here we have bin weights. Okay, so there we have it. Let's have a look. Great, so you see now that we have weights, okay, weight values associated to different, say, gradients, okay? So depending on the position of the gradient, whether they are closer or farther away to reference orientation, well, they are going to be greater or smaller, okay? The closest they are to a reference orientation, to a given reference orientation, the higher they're going to be, all right? Well, you'll see that we still need to do some work on these weights, okay? But yeah, for now, that is the first block, okay? That is the way of obtaining the bin weights, all right? Essentially using the formula, the direct formula for arc cosine, okay? But say that we are having problems. Of course, here we're not having any problems because we have very few data and everything goes fast. But let's say we're having problems, okay? Let's say we are struggling to compute or we're struggling to extract the angles associated to these gradients. And in that case, we would use, okay, the approximation of the arc cosine, okay? So let's do that right now. So in case that essentially the first method is not, say, the best option, we use the approximation. So let's go ahead. So how do we proceed? Well, we start with the same way because of course we need to pre-process the cosines, just like we did with the above block. All right, then, well, again, we're going to pre-process this and let's visualize that. I'm going to put here method 2 to distinguish. Of course, the first block is not going to print out. Well, yeah, just so that we keep in mind that we're dealing with the second block. Yeah, so you see perfectly, we obtained the say clamped cosine values. Yeah, great. So what is next? Well, again, we follow the same idea. We need to extract the angles, but now we are going to use the approximation. Okay, so the approximation is if you perform the Taylor expansion, of your arc cosine, you'll see that you are going to obtain, yeah, the value of square root of 2 times 1 minus x. Okay, so our cosine is going to be approximately equal to square root of 2 times 1 minus x. Well, how did we get this, or how can we derive this? Well, you need to start from the Taylor series expansion, okay, for a smooth function f of x, okay, around a point x is equal to a, okay. Well, in this case, we are going to use around the point x is equal to 1, okay. So we know from calculus the formula of the Taylor series extension, and we're just going to focus on the first derivative. Okay, so we are just going to be working with the function f of a and f prime of a times x minus a. Okay, and essentially we're going to essentially we need to take the first derivative, and if you evaluate the first derivative using the point x is equal to 1, you'll see that you get a singularity, of course. Yeah, and we need to deal with this. We need to deal with this singularity. And how? Well, we need to explore it. And how do we do that? Well, we need to define an x. Okay, we need to just simply say, okay, instead of evaluating x is equal to 1, we are going to evaluate x is equal to 1 minus epsilon. Well, where epsilon is going to be a very small number. Okay, so if you apply this, say, approximation, right now we're looking at a neighborhood of x is equal to 1 that it's very, very nearby. You'll see that we can approximate 1 minus x squared, okay, which is the term that is in the denominator of f prime. You can approximate it to be 2 times epsilon, okay? And once you have that, well, you simply can go to the function and essentially perform the algebraic operations to obtain the arc cosine is approximately equal to square root of 2 times epsilon. But again, I didn't want to show it here because we want to focus on the code here on these sessions. But of course, feel free to leave a comment if you would like me to show it like on the blackboard. Okay, great, fantastic. So let's continue. So let's implement this essentially approximation. And how do we do that? Essentially, well, of course, we need to define a new angles variable, and I'm going to call it angles. As the approximation is embedded in the square root, let's just call it square root 2. Implement it. So square root, and as we said, the approximation is going to be the square root of 2 times 1 minus the values of the cosines. Okay, remember these values are numerical values of the cosines, not the angles associated to them. Okay, this is what we're doing right now with this formula. Fantastic. So now what is the third step within the block? Well, as we did above, well, let me actually first state here that we compute using Taylor expansion of our cosine. Okay, in first order. Okay, and there we have it. Fantastic. So what is next? Well, as we did above, we're going to map the angle to a weight, and the actual formula is essentially the same. All right, essentially the same. So what we do here? Well, remember the angles now are called differently. Fantastic, but the rest is the same. Okay, so now we also print the results. Fantastic, and we also want to print the well, no need to print the angle approximation. Okay, right now what we can do is just to print it out. Yeah, so weights associated to angles, and I'm going to put here a method too, so that we keep in mind that we are using the second method. Okay, so let's run this. And there we have it. There we have the weights that are associated to the angles using the second method. Okay, using the second method. Oh, fantastic. So actually, I am curious to, essentially pursue this further. Yeah. So let's continue. So now we just got the weights, and just for the sake of this exercise, let's continue with the second method, okay? Let's continue with the approximation. Okay, so now, but again, what we're gonna do now could be equally done with the direct method, yeah? So now we see that in both cases, in both methods, we obtain, okay? So essentially, we observe that we get negative weights, okay? We see that we get negative weights associated to our angles. And if you have a look here, and instead of selecting the second method, we select the first, you're gonna see as well that we get negative values, okay? That we also get negative values, okay? So this is telling us, that we need to preprocess further the weights, okay? So we need to preprocess the weights now, because we cannot be dealing with negative bin weights. And the question is, why do we need to get rid of the negative weights? Okay, so essentially remember that the whole point that we've been doing in the last 3 videos or so is to define the histograms of array gradients. Yeah, so these histograms, okay, what they do essentially is to aggregate magnitudes of gradients. The magnitudes of the gradients, yeah, and the magnitudes need to be always positive. Okay, the magnitudes of the gradients, they need to be always positive. Hence, the weights that are associated to these, say a magnitude of gradients, they need to be positive as well. So, or at least better say, they need to be non-negative. Let's call it that way. So, how are we going to fix this? How are we going to get rid of these negative bin weight values? Well, we're going to clamp them out. And how? Well, we're going to replace all negative values by zeros. Okay, so that we avoid having to deal with negative weight values. So let's do that. So we're going to get rid of negative bin weights. Okay, exactly. So essentially, we're gonna do just that. So first of all, we need to store our filtered bins, our filtered bin weights. Yeah, and we're gonna clamp. We're gonna clamp the bin weights. We need to clamp the bin weights in a way such that we get rid of the negative values. Fantastic. Yes. So now, let's also visualize them. So say clamped bin weights, and bins here. Great. So fantastic. So you see how now we do not get negative values. We just got rid of these negative values and we replace them by zeros. Okay, because again, these clamp bin weights are not going to be dividing, at least for now in this specific function, in this specific method, any value. So it's fine to get zeros within clamp bin weights within this method. Okay, great. So what is next now? Well, what we need to do is just to multiply the bins, the filtered weight bins, by the norms. Okay, by the norms. Why? Because you need to think of weights as scaling factors that are going to basically tell us whether a certain gradient is close or not to a given, say, orientation gradient neighbor. Okay, and to do that, yeah, we just need to scale the gradients. We're going to scale the gradients of our image, yeah, by the bin weights. Okay, to find out what we just said here. Okay, so return norms times bins, and that is going to give us, and let me comment everything out because we have already visualized through. So so that we can clearly see the output. So, and this, get rid of this. Fantastic. Great. So these are basically the angular bin results. Okay, basically the gradients after passing through the angular binning method. Okay, and remember what these gave us. Yeah, we explained here. What this gave us was a score that would essentially tell us whether a given gradient, okay, would be close enough to reference orientation or not. Okay, so for example, imagine that our reference orientation is 40 degrees. Yeah, and our original gradient is 30 degrees. Hence, the associated score, the associated, say, angular binding value is going to be greater as compared to, for example, the same gradient, okay, being compared to the reference orientation of 0. Okay, it's going to be lower value. All right, so that is the logic behind it. But don't worry, because again, it's the first time that we saw this, the first time that we defined it. But as we progress, we'll see it applied in, say, more clear context, and it will become even more clear. Okay, but yeah, that is all I wanted to discuss in this video. I hope it was helpful, and I am willing to see you very soon.